Hi, I'm Dr. Christopher Sutton. Welcome back to my Introduction to GIS video series. In this video, we will examine proximity operations. Proximity operations allow us to explore spatial relationships by measuring how features relate to each other in geographic space. Proximity operations analyze spatial relationships based on distance, helping answer questions like, what is closest to X? What falls within a certain distance of Y? How far apart are two features? In proximity operations, distance measurements are critical. There are three commonly used distance measurements that we use. The first is Euclidean distance, also called straight line distance. Euclidean distance is the shortest distance between 2 points on a plane. It is calculated using the Pythagorean theorem. We use Euclidean distance for measuring distance across small areas. Geodesic distance, also called great circle distance, is the shortest distance between 2 points on a three-dimensional surface. It's used for measuring distance across large regions or continents. There are two ways to calculate geodesic distance. One is to treat the Earth as a perfect sphere. When we calculate distance on a sphere, the Haversian formula is used. If we treat Earth's shape as an ellipsoid, we use Vincenti's formulae to calculate distance. The third kind of distance measurement is what we call Manhattan distance, which is also known as taxicab distance. It is the distance between 2 points measured along axes at right angles. It's used in network modeling, especially movement on a grid. Here we can see 2 points that exist in a space where we have a regular grid. The straight line distance between these two features is represented by this dashed line. If the lines of this grid are actually streets and this is a city, we can't travel between the 2 points in a straight line. We have to use the streets. Manhattan distance is the calculation of distance along the network between the 2 points. This image shows the Manhattan distance on a regular grid. Cities, however, oftentimes do not have uniform regular grids. They might have a network of streets that looks like this image. Calculating Manhattan distance in this network might result in a path that looks like this, represented by the blue line. If proximity operations are based on distance measurements, what are the actual operations that we use? One of the most common proximity operations is buffering. Buffering involves creating an area around a map feature whose perimeter is determined by a set of points at a specified distance from the feature. Buffers are very useful in GIS. For example, we could create a buffer zone around a river to help in flood risk assessment by identifying all lands within a certain distance that might be affected by flooding. Let's break down how buffering works. Here we see a feature. This could be a road, for example. If we're going to create a buffer around this road, how do we do it? We start with identifying the vertices of the feature. So these are the locations where our line changes direction. We use vertices to create what are called buffer offsets. Buffer offsets are essentially a circle of points at a uniform distance from the vertex. We use the outermost offsets to create the buffer. If we remove the vertices and offsets from our image, we have the buffer as you might see it created using GIS software. This is an example using one feature. You can create buffers around multiple features inside of a data set. One of the things that occurs when you do this is that buffers may overlap each other. So how do we deal with overlapping buffers in our analysis? There are two ways. The first way is to do nothing, is just to leave every buffer as an individual polygon that has been created around a feature in the data set. The second option is to use dissolve. Dissolve removes overlap between features and removes any internal boundaries that are created by the overlap of the buffers. Here we can see 3 buffer areas that are created without dissolve being turned on and with dissolve being turned on. The buffer that I showed you in the example is a fixed distance buffer, meaning that we create a buffer around each feature using a specified distance, and we would use the same distance for buffers around all features. Here is an example from the Denver area. What we see in the map are the locations of fire stations. We might want to create buffers that are 1 mile from the fire stations. If we generate them without using dissolve, our buffers look like this. If we create the buffers and we use dissolve, then the buffer polygons look like this. It may not be easy to identify where buffers have been combined with each other, so let's turn off the symbols for the fire stations. Now we can more clearly see where the buffer polygons have been merged. A variation on fixed distance buffers is what we call multiple ring buffers. As the name implies, multiple ring buffers are when you create multiple buffers around features using 2 or more specified distances. Here are the fire stations with buffers at a 1/2 mile, 3/4 of a mile, and 1 mile. In this map, we see them without dissolve being used, and here we see them with dissolve being used. Again, I will remove the fire station symbol so we can see how dissolve results in merged polygons at each of the 3 distances. Another variation on fixed distance buffers is what we call negative buffers. When we make a buffer around polygons, the buffer is created at a distance outside the polygon. But there are instances where we might want to create a buffer and have it be inside the polygon. When we do this, it's called creating a negative buffer. The way to do this in the software is to use a negative number to indicate the buffer offset. Using a negative distance will place the buffer inside the feature. Let's look at an example. Here we have parcels in a city, and let's say we have a city ordinance that prohibits structures within 10 feet of a property boundary. To create a negative buffer inside the polygon, we would specify a distance of -10 feet, which will give us an output that looks like this. The areas in yellow are the areas inside each parcel where structures are prohibited. In addition to fixed distance buffers, we also have varying distance buffers. What this means is that we use different buffer distances based on feature properties. We use a field in a layer's attribute table to specify the distances. Let's say, for example, we have a road layer and we have different kinds of roads, city streets, township roads, US highways, and so forth. And we want to create buffers, but we want the buffers to be based on the category of the road. The US highway buffers would use a greater distance than, say, city streets. Here is an example of using varying buffer distances on the same layer. In this case, I had a field in the attribute table that specified the buffer distance based on the road type. Well, this is how buffers work, but how do we actually come up with how big a buffer should be? Well, there are 3 primary ways of defining buffer size. One is what we call arbitrary buffering. As the name implies, we're just using an arbitrary number based on our best guess of what we would like the buffer size to be. Causative buffering is when we create buffers based on some knowledge of the landscape or conditions surrounding the features being buffered. Finally, there's mandated buffering, where standards for buffers are defined by federal, state, or local government agencies. For example, flood zones or sidewalk easements. In addition to buffering, another commonly used proximity operation is the spatial join. Spatial join joins attributes from one feature class to another based on spatial relationships, which can include distance-based proximity. Examples of spatial joins can be assigning each household its nearest health clinic, where households are represented in one feature class and the health clinics are in another. We can use spatial joins to count the number of restaurants that are within 500 meters of each school in our school district. Or we can count how many tornado touchdowns occurred in each of a state's counties. Another spatial operation is the creation of what are called Tyson polygons. Tyson polygons are polygons that divide an area into regions, where every location within the region is closest to an input point than any other input point. This may not make a whole lot of sense in its description, so let's look at an example. Here we have Chicago and some near suburbs of Chicago, and we're displaying hospitals. When we create Tyson polygons, we end up with these polygons which define space where every location inside each of these polygons is closest to the hospital that the polygon surrounds than to any other hospital. We can use Tyson polygons in emergency services for planning the locations of facilities such as fire stations, hospitals, or police stations. Tyson polygons can show the area closest to each facility, helping in analyzing response times and coverage. This can guide decisions on where new facilities should be located to optimize access for the entire population. We use Tyson polygons in retail analysis to define trade areas for stores where customers will naturally go to the nearest location. And we can use Tyson polygons in ecological studies to define territorial ranges for animal species based on nesting locations. Another proximity operation is the near operation, which is used to calculate the shortest distance between features. If we go back to our hospital data and specify a point which is indicated on the map by the red X, we might use the near operation to determine which hospital is closest to this location. When you do this in the software, you can specify only which is the nearest hospital, but you can also say, what are the 20 nearest hospitals? And the output will be a table which shows the nearest 20 hospitals and which one is closest, second closest, third closest, and so on. Understanding proximity operations is essential for applications like urban planning, emergency response, and environmental monitoring. With proximity operations, we can answer questions like how far, how near, or what lies within a certain distance. In the next video, we will wrap up our introduction to vector GIS operations by looking at overlay operations.